Should I start? Yeah. Okay, now that I'm here. Okay, so we're going to proceed with entanglement in field theories. Seems a little loud. I'm going to lower this. Is that okay? So where we were at last time, we had been studying Rindler space, which is a simple case where our region A was half space. Tangling surface is a plane at t equals 0. And using Euclidean path integral, we had derived this formula for the density matrix, which tells us that the modular Hamiltonian is 2 pi times the generator of Euclidean rotations, which is the same as the generator of boosts, as the Lorentzian generator of boosts, and indeed the boost generator acts within the Rindler wedge, or Rindler space, which is d of A. And so this is a nice explicit formula. It's the integral of a local, very familiar operator. And so it tells us, because we know how this generator acts, we know that we can interpret this as a thermal state. Of course, anytime you write rho sub A equals e to the minus h sub A, you can think of it as a thermal state. But here it's a thermal state with respect to boosts at a particular temperature, 1 over 2 pi. And that implies, so first of all, I should mention that this equation was written down by Bisignano and Wichmann in 75, following work by Unruh. And one thing it implies is that if you're an observer and you stay at a fixed, you basically stay at a position, or let me say it this way, you are static with respect to boosts, meaning your world line follows a trajectory which follows a hyperboloid. So this is an observer who stays at fixed boost invariant distance from the entangling surface. So L that observer, as far as they're concerned, they're at a temperature 1 over 2 pi, but there's an x1 here. So let's say it's at time x equals 0, time t equals 0. As far as they're concerned, they see a local temperature, a local physical temperature. So the temperature with respect to k is always 1 over 2 pi, but the physical temperature with respect to their proper time is 1 over 2 pi L, which has the right units. Okay, and this leads to, or is one way of understanding, the Unruh effect, which says that such an observer who's carrying a thermometer will actually measure this physical temperature, and you can study the response of a particle detector, for example. An accelerating particle detector actually sees particles even in the vacuum. It's the famous Unruh effect. And this is one way of understanding it. And one thing it tells us, so when I said that the observer who sees only the region A, for them the world is in a mixed state, you could start arguing about whether or not that's physical. Does it lead to any physical effects? Well, yes, I mean, that's a very physical effect. So this observer carrying a thermometer measures a temperature. And for that observer, there's an actual physical temperature. So there's no question that the world for that observer is actually in a mixed state. So you have actually produced some real physical decoherence that has produced a real physical effect. And we can use the Unruh effect to estimate the entropy. So let's say I have a field, and one thing this implies is that the closer you are to the entangling surface, so the smaller L is, the hotter the temperature is, the higher the temperature is. And so the fields close to the entangling surface are very hot. So this is a very hot region in here. And the reason for that, heuristically, is that the closer you are to the entangling surface, the more you see the decoherence of the short wavelength mode. So we've done a very violent thing to the field theory by cutting it at a spatial position, which means that all modes have gotten split into two pieces. And the closer you are to the entangling surface, the more you see the effect of the UV modes having gotten split. Okay, that's just a heuristic way of understanding why the closer you are to the entangling surface, the more sensitive you are to the decoherence of the UV modes caused by this split. Okay? And we can use this fact to estimate the entropy. So assume we have a massive field. And I'm going to use something that Oliver mentioned yesterday about the entropy density. So the entropy density as a function of temperature, so little s as a function of temperature, roughly speaking. So we're going to do a somewhat crude estimate. If the field has mass m, then if the temperature is below the mass, then roughly speaking the entropy density is 0. Because the field, there's not enough temperature, enough thermal energy to excite the field. If it's above m, then it's t to the d minus 1, just from dimensional analysis times, some kind of central charge. Okay? So using this estimate, we can estimate S of A. So basically, I'm going to pretend that the entropy, so what we have is not a system that's fully in thermal equilibrium because different positions have different temperatures. I'm just going to estimate the total entropy by adding up the entropy on different positions. Okay? So I'm just going to add up the entropy here, the entropy here, the entropy here, and so on. And that would be fine if they weren't, of course, interacting with each other. Okay? But so you get integral d minus 2x, integral from 0 to infinity dx1 s of t, which gives you the area of the entangling surface, sigma. Okay, times, now here the problem is if you plug this in, with t equals 1 over 2 pi x1, you get a divergence. And so I'm going to cut it off here, some epsilon. Okay, so we get integral from epsilon only up to 1 over m dx1. So essentially, the fields past x1 equals 1 over m are not excited. So the integral is only from epsilon to 1 over m of x1 to the d minus 1. And if I did this integral correctly, this is 1 over epsilon to the d minus 2 minus the mass, to the d minus 2. And I just want to say that we reproduced what we got before from the sort of spin block picture where the mass is, of course, now 1 over the correlation length. Okay? So you can get the same estimate from just adding up the local entropies. Okay? That's essentially, if you want, that's the content of this estimate of the entanglement entropy. Okay? So in some sense, it's, it's sort of a 0th order estimate. And then if you want to go beyond that, of course, you have to look at a specific field theory, and it becomes much harder. And that's what we're going to do next. Yeah?
Yeah, minus
Oh my gosh. Is that better? Okay, thanks. To do better, to be a little bit more precise, let's give ourselves a helping hand by adding more symmetry. So I'm going to talk about 2D CFTs. Now, of course, here, by the way, had I been in 2 dimensions, I wouldn't quite have gotten this. The previous estimate, so let me do this down here. In D equals 2, I would instead have gotten, there's no sigma there. I would have instead have gotten minus log m epsilon. And so if I want to take the limit of a CFT, not only do I get, of course, the UV divergence from epsilon going to 0, but even if I fix epsilon, from m going to 0, I get another divergence. Okay? And that divergence is from this point of view an infrared divergence, because now my 1 over m has gone off to infinity, and I'm collecting entropy all the way out to x1 equals infinity. So let's cut that off in order to get a reasonable looking answer. So IR divergent as m goes to 0. So we're going to just consider a finite interval. Something that looks like this, and something of length L. Okay? And now let me again do this same kind of estimate. So now I can be a little bit more precise here. My entropy density in a CFT. Okay, so I want to say something here about why I'm doing this. We're going to get an answer by this estimate, and the answer can be obtained by many other ways, and we'll see a couple of them. But often entanglement entropy calculations turn into a bunch of formal tricks. And I want to do this case in this kind of very simple-minded point of view. It actually gets the right answer, so that you understand that this entanglement entropy is an entropy that you can calculate thinking about it just by adding up local entropies. Okay? And so I want to try to give some kind of physical picture of what this, so it doesn't just end up being, okay, you do some complicated calculation, you get an answer. Okay? The entropy density in a CFT, in a 2D CFT, we can be quite precise about as a function of the temperature. Is precisely this, it's not approximately. Here's my central charge. Okay? And so if I plug that in, I find that the UV divergent part, so the part I get just from integrating up to some epsilon on one side, so near an endpoint, the endpoints are the dangerous places, is the integral from down to epsilon of this. Okay, and once you plug everything in, you get this, c over 6 log epsilon. And I have 2 endpoints. And so that means I have minus c over 3 log epsilon. And now I can use dimensional analysis, because in a CFT, I have no other dimensionful parameters except for the length. But the entropy is dimensionless. Okay? So S is dimensionless, which implies that S of A must be, the only thing I can have is some epsilon over L here, so it must be C over 3 log L over epsilon. So by combining dimensional analysis with this estimate of the UV part, I get my answer. Okay? It's by far the easiest way to compute the entanglement entropy in a CFT. Okay? Now, we can say more. We can do the Euclidean analysis that we did for Rindler space because we have now a conformal symmetry. And by a similar analysis, you can say that the reduced density matrix looks like this. Well, okay, so at this stage, so some path integral over Euclidean space with a cut on A and inserting phi prime and phi on the top and the bottom of the cut. So this is the same analysis where you have basically the ground state is prepared by a Euclidean path integral in the half space. This state is prepared like this, and then I integrate over everything except A. So this I fill in when I do the trace over A complement. I fill in here, and I'm left with a gap there. Okay, so this is true in any field theory. I haven't used the conformal symmetry. But now you can see that actually the top and the bottom here are related by the action of a conformal isometry, a conformal transformation, which is generated by essentially a conformal rotation. So I have a formula which is very similar to what we had before, where K is a generator of the conformal transformation, which acts like this, which goes around like this. This is some combination of a special conformal generator and a boost and dilatation. It acts like this in Euclidean space, and in Minkowski space, it acts like this. Basically, so in Euclidean space, near the endpoints, near the entangling surface, it's a little Euclidean rotation. And near the entangling surface in Minkowski space, it's a little boost. And it acts within the causal diamond because it acts on, or yeah, you can think of K is an operator on the Hilbert space of A. The Hilbert space of A basically corresponds to the causal diamond of A. And so it's a little kind of boost inside, which does like this. So sort of, if you want, you can call it a conformal boost. And we can actually write a formula for it. I didn't give myself enough space. Well, hopefully it's clear. Okay, and so again, we get from this a position-dependent local effective temperature, where the temperature is smallest in the middle, it doesn't go to zero anywhere, and it goes to infinity at the two endpoints. At the two endpoints, you think you're basically in Rindler space. Okay. Now, in the two cases we've seen so far, the Rindler space and a single interval in a 2D CFT, the modular Hamiltonian, which was 2 pi k, is the integral of a local operator. And you might get the impression that this is usually the case based on 2 out of 2 examples, but it's actually very, very rare. It's due to the very large amount of symmetry we have in these cases. So very few. I mean, there's more than this, and it can happen again in higher dimensions, as we'll see, but it's definitely the exception and not the rule. Yeah? Oh, I was just trying to extract the UV divergent part. So the epsilon dependence. Because if I know the epsilon dependence, then I know the L dependence by dimensional analysis. Now you could do something different. What you're saying is do what I was saying before and actually do the integral from epsilon to L minus epsilon. You'll get the same thing up to, and in fact this is maybe a good place for me to say this, up to some constant, which I don't know. So the truth is that, and you can actually see it from here. Let's say I just redefine epsilon. Say, my epsilon is half of your epsilon. So do we agree on the entropy? No, we disagree by C over 3 log 2. And so the finite term, so there's a finite term here which is undetermined. Okay, so plus a non-universal finite term which crucially is L independent. And so if we have slightly different procedures, regularization schemes, for computing this, like I had one and you had another, and we got slightly different answers, and in particular, this part will differ, but the difference will be L independent. It has to be because it's epsilon independent, because it's finite.
Why does something epsilon over L?
And of course, I'm not, I'm taking epsilon to 0, so I don't care about stuff that goes to 0 as epsilon goes to 0. Okay. Oh, this is wrong. Wait. Oh, no. Yeah, okay. So this estimate was only correct. So this is a formula for the local temperature, which is only correct near one of my entangling surfaces. Yeah. So I think if you plug my correct formula for the local temperature, which is 1 over this coefficient here, I think it should all work out. Okay, now you may want an honest calculation of the entanglement entropy, and there are various ways to do that. So one way is I write this formula. Since I'm lucky enough to have a formula for my modular Hamiltonian, I might as well go ahead and use it. And in fact, life simplifies when I use it because my modular Hamiltonian up to a 2 pi is an integral of the stress tensor, and the expectation value of the stress tensor in the vacuum is 0. So in fact, this is 0 in this state. And so now it just comes down to calculating log z. But of course, you have to be quite careful how you do that. I mean, of course, there's, we're manipulating UV divergent quantities. And so one way to do it is we do a Vial transformation on this. So we map by a Vial transformation this to a cut sphere. Let's see if I can draw this. Okay, so I've made a little cut. In fact, I don't really need this part. So I have an S2, which I've cut open, and this is one of these, and this one is the other one. So because this thing is basically living on it's a cut sphere, and so I can write it like this. And under a Vial transformation, my partition function, so if this is the partition function is what I want here, and here, oh, sorry, I should have said, of course, the partition function is the trace of this. This is an operator. And the trace of that operator is just gluing this together, and I get a sphere. And the trace of this operator is gluing this together, and I get a sphere. And in particular, if I choose, as I can, to make this a unit sphere, then I can consider that to be like a standard L-independent, to have an L-independent partition function. And then where does the L-dependence come from? The L-dependence comes from the transformation of the partition function under a Vial transformation, which is given by the Vial anomaly. And the Vial anomaly says, if this is Z S2, we have this relation. The Z we want is e to the c, well, e to the Liouville action times Z on S2. And this thing you can go ahead and calculate. And this thing is proportional to C. I won't write it down. It's proportional to C, and it's an integral of basically the derivatives of the Vial factor. And you can just write down what the Vial factor is. It gives you this transformation. Then you can go ahead and calculate this Liouville action. And then that tells you exactly log Z. Up to log Z on S2, on the unit S2, which is this non-universal L-independent piece. Okay? I'm not going to do that. Yeah. There was a question. Yeah. How what? The Vial transformation oh, sorry. This is divergent. So it's funny that you get an L dependence in this and an epsilon dependence in this. And then they combine to give you this log. Okay. I'm not going to go through that calculation. I'm going to show you a different way to calculate it, which is more general and more powerful, and doesn't rely on, basically doesn't really rely on, or at least not in all of its steps, on having such a simple setup. Okay? And the way is to go via the Renyi entropies. So we want to calculate, was there a question? We want to calculate trace rho A to the alpha. Okay? And if we can calculate trace rho A to the alpha, then we know the Renyis, and if we can fit that to an analytic function, we can take alpha to 1 and get the von Neumann entropy. Well, okay, here we have a representation of rho A in some particular basis, and so we can certainly square that and cube it, and so on. So, like, if I want rho A squared, I just take 2 copies and I glue the bottom of one to the top of the other. This should be regarded as an operator. If I want to calculate its matrix element, I put the bra on this side and the ket on this side and calculate the partition function on this surface. Okay, and that gives me the matrix element of rho A squared. Okay, and similarly for cubed, same deal. Okay, etc. And then the trace is now, since I had my two open surfaces, edges, I glue them together. Okay, so I mean, what is this thing? This is a three-sheeted Riemann surface with a cut. So in general, alpha sheets with a branch cut at 0 and another branch cut at L, such that when you cross the branch cut, you jump down to the next sheet. Okay? So it's like the Riemann surface for this equation, I think. Z to the alpha equals x times L minus x. It's the Riemann surface for that equation. Okay? And now we want to, so now it's 1 over z cubed times the partition function on this Riemann surface, which can be computed in various ways. I mean, then it becomes a CFT problem, computing a partition function on something. And actually what it is it's still a sphere. Okay, this Riemann surface is still a sphere, and so it's actually kind of related. It's a different way, but it ends up, the problem is to compute the partition function on a sphere, which is just written in some horrible coordinate system. Another way to think about this is that because we have alpha sheets, we can actually think of it as alpha copies of the same CFT, which has been orbifolded to allow twist operators that take us from one copy to another. So whatever our original CFT was, we have a copy of it on each sheet, and then we orbifold by the cyclic permutation symmetry, and that introduces twist operators, and the twist operators are such that if you go around a twist operator, you jump from one copy of the theory to another. So this partition function can be written as an expectation value of twist operators in a particular orbifold CFT. So let me call this Z alpha. Whoops. So let me just say to the alpha, this is Z alpha. And Z alpha is can be thought of as a two-point function of two twist operators in the orbifold CFT. So in this theory, C to the alpha mod Z alpha. So this is my original theory. Take alpha copies, mod out by the cyclic permutation symmetry. So not the full symmetric group, but just the cyclic symmetric group. Just the cyclic group. And then that introduces twist operators, and a twist operator has the property that if you go around it, it's kind of like a monopole operator. If you go once around it, you jump from one copy to the next copy, if I label my copies from 1 to alpha. And so now I have such a twist operator, and I have its conjugate, which takes you the other way, which generates the cyclic permutation in the other direction, and I've just introduced 1 sigma and 1 sigma bar. And so now we're in the land of computing CFT correlation functions, which is something we have a lot of technology for, especially two-point functions, of course. Okay? But the point is that if you want to do something more complicated, this is a more powerful technique than this sort of approach because let's say I wanted 2 intervals, then it would be the same deal, but now it would be a 4-point function of twist operators, which admittedly is harder, but at least now I have some CFT technology for computing things like that. Okay? Whereas in that case, I have no expression for the modular Hamiltonian, and there's no hope of doing either, the estimate I did on the other board, or this, where'd it go, or this way of thinking about it. Okay? Okay. So this is, was there a question? Yeah.
I was curious if you could, for like a free boson, just for example, what this twist operator looks like.
Well, what the twist operator looks like, what I said is what it does. I mean, it's not something that you can write in terms of the elementary fields. It's like it's quite similar to like an 't Hooft operator in a gauge theory, where inserting the operator puts a boundary condition on the fields in the path integral, as opposed to returning the values of the fields in the path integral, as opposed to giving the expectation value of the fields in the path integral. So what it does is it says you have these alpha copies secretly. So on each point here, you actually have alpha copies of your field labeled in some way, let's say from 1 to alpha. And inserting this operator means that, so in general on the path integral, you're doing the path integral independently for all alpha copies of your fields. Okay? But now you have a constraint, and of course, as usual, like on a single sheet, in a given configuration in your path integral, if I go around in a little loop, I get back to the same value. But now, if my loop encircles a twist operator, I don't. I get back to the value on the next copy in my alpha copies. Okay? Yeah?
Also, if we inserted 4 of these, how does it know to pick out a particular branch structure we want?
It doesn't, and it doesn't matter. But what does happen, I mean, 2 of them are sigmas and 2 are sigma bars. You would have like sigma, sigma bar, sigma, sigma bar. And that's all the data you need to compute it.
But I can connect either sigma or sigma bar, but I want to.
Yeah. It doesn't matter. They have the same correlation function. Correlation function doesn't depend on how you connect them, as long as you connect a sigma to a sigma bar.
So why you need to mod out by C alpha?
Because I want there to exist these twisted sector operators. So this theory does not have any twisted sector operators. This is just alpha independent CFTs, and it doesn't contain an operator that does what I want it to do. But once I orbifold it, it now contains this operator. Okay? And furthermore, you can calculate, so in this case, it's just a 2-point function, and that just depends on the scaling dimension. And I'm not going to go into it, but there are easy ways to compute the scaling dimension of sigma. So this is sigma at 0, sigma bar at L in this theory. And delta sigma is C over 12 alpha minus 1 over alpha. And so we get that this thing is L. And these are, okay, how did the epsilon come in? Because you have to renormalize. So there's the bare sigma operators and the renormalized sigma operators. The renormalized sigma operators are the ones that have 2-point function equal to 1 at distance 1. But the bare operators are related by epsilon to the scaling dimension to the renormalized operators. Okay, so some technical annoyance there that, if you think about it long enough, becomes fairly clear. From this, we get S alpha. So you have to take a log of this, and you have to subtract off the log of z times alpha, and you get this famous formula. Well, wait, not yet famous. It's going to be famous in a second. For the Rennies, And therefore, okay, and now I hope you believe me that the analytic continuation, so we only calculated this for alpha equals 2, 3, 4, and so on. And now we're going to be good physicists and not think too hard about how to analytically continue it. We're just going to stick in alpha equals 1 in the formula. And we get C over 3 log L over epsilon, which is what I got before. Okay. And this was first derived by Holsey, Larson, and Wilczek in '94. Okay, this is maybe the most famous calculation of an entanglement entropy in a field theory. Okay? Now, now that we calculated it, why do we care? Well, for various reasons, but let me just emphasize that in practice, this is actually a very useful formula. If you have a spin chain, which you hope is describing at long distances some critical system, and so you've tried to tune your parameters to criticality and so on, how do you really know whether you're on the critical point and if you are, what CFT you have for your particular spin chain? So one thing you can do, which is actually one of the easiest ways to answer this question, is you calculate the entanglement entropy of an interval or a family of intervals in your spin chain and see whether it has a logarithmic behavior. And if it does, that's good evidence you have you actually have a critical spin chain. We're going to see in a minute what it looks like when it's not critical. So if you have a log, that's a diagnostic of criticality, and furthermore, you can just extract numerically the central charge. This is one of the best ways to extract numerically the central charge from a spin chain. You might think, oh, let me just calculate a two-point function of the stress tensor, but in a spin chain, actually, it's not obvious what the right stress tensor is in terms of your spin variables. Whereas here, you don't need to worry about that. You just compute this, which is well-defined, and then you fit to a log. Okay? Okay. Now, you can spiff up this calculation without too much trouble to introduce finite temperature. At finite temperature, now your Euclidean picture is on a cylinder, and so you're computing this two-point function of twist operators now on a cylinder, but a cylinder in CFT is still a sphere, and so you can still compute that exactly, and you get this. Well, why don't I just draw a picture? And this thing has circumference beta. Okay, and then you do your CFT calculation. So all the machinery is set up, and you just apply your CFT tools, and you get this. And let me, perhaps it's more useful to plot it. So L. Okay, and what we had before, so at 0 temperature we had a log. And now if you take L large, much larger than 1 over t, log sinh becomes linear, and so you get something that looks like this. At small l, it doesn't really know it's at finite temperature, but above 1 over the temperature, you get a linear contribution, and the linear thing, guess what? The coefficient is 2 pi c t over 6, which is the thermal entropy density for CFT that I told you before. Okay, so this is the extensive, so times L, extensive thermal entropy density. Okay? Since we're doing it on a cylinder, let's make the cylinder spatial instead. So on a circle, so then now my space is a circle, and I again have sigma and sigma bar. And it's a two-point function on a cylinder, which again is a sphere. And so again, you can compute it. And basically, you won't be too surprised to learn that essentially what happens is that the sinh becomes a sine. So this is, let's say this is R. Then we get this formula. C over 3 log 2R over epsilon sine L over 2R. And that looks like this at first. So now we have a length scale R. Let's say the biggest L can be in this setup is 2 pi R. And it looks, at first, for a very small interval, it doesn't know it's on a circle. And so it looks the same, and then it goes back down again. Well, doesn't hit at 2 pi R. Whatever. And it peaks at pi R. And so here, so I should say, yeah, if you have a large A, so if you're on a circle spatially, and here's A, and let's say A is actually almost the whole thing. Well, in this case, I'm at 0 temperature. So these were two separate things, back to 0 temperature in this case. If you're at finite temperature and on a circle, then you're on a torus in Euclidean space, and then your life is much harder. Okay? Then you're doing two-point functions on a torus, not two-point functions on a sphere. And you have to work much, much harder. And in particular, the answer will depend on which theory you have in a much more complicated way than just being proportional to the central charge. But here we're at 0 temperature, which means we're in a pure state. And in a pure state, S of A equals S of A complement. A complement being this little bit. And that's why it's symmetric under L goes to 2 pi R minus L. And also we see it's going back down, which means your conditional entropy, if you take like a larger interval with respect to a subset of it, the conditional entropy, the larger interval will have a smaller entropy than the subset, which means we have a negative conditional entropy. That's the first calculation we've seen so far that looks like that. So that's interesting. And now let me do one more 2D generalization. Where I now say, okay, what if it's not conformal? What if it's massive, for example? Well, now it becomes much more complicated to make general statements, but we would expect, in fact, maybe I'll plot it on the same thing. So let's say you have some mass. Let's get a different color. Well, for an interval that's much smaller than 1 over the mass, then essentially this Rindler discussion should apply, and I should get a log epsilon times the mass. Sorry. I take that back. Sorry. Let me start over. Okay. So I have a single interval in a massive theory of length L. Okay. Now, if L is much smaller than the correlation length, then I should get then essentially the theory thinks it's still a CFT. As far as distances very small compared to the correlation length are concerned, let's say the theory has it comes from a UV fixed point, which is a CFT. Okay. then the entropy for intervals that are very small compared to the correlation length should follow this log L over epsilon. For intervals longer than the correlation length, we have this estimate I did for Rindler space before, where essentially after a certain distance, the entropy saturates. Okay, so for L larger than the correlation length, it saturates as if L had been the correlation length. So you don't get more and more entropy from having a longer and longer interval. So it looks like this. At small L, it follows the curve for a CFT, and then at some point it saturates. Okay, that point being, I shouldn't have had all these sitting on top of each other, being the correlation length, or 1 over the mass. Okay? Now, this has actually been computed, this curve has been computed for free bosons and free fermions using a combination of analytic and numerical techniques by Cassini and Huerta. And in non-free theories, it's much harder, although some calculations have been done. And, you know, it basically looks qualitatively like this. Okay? At short distances, it looks like a CFT. At long distances, it saturates. Now, there's something you can notice about all 4 of these curves. Besides the so for one thing you notice is that for small L, they all look like log L over epsilon. But there's something else you can notice about their behavior. You can't say they all increase. That's not true. But what is true about all of them? They're all concave, negative second derivative. Okay? Or non-positive second derivative. That's not an accident. That's a consequence of strong subadditivity, which you can see as follows. So let me make B sort of long and A and C infinitesimal. And then strong subadditivity can be written in this way. This is essentially the first derivative. This is also the first derivative. And this whole thing is the second derivative. Okay, ABC minus BC. That's the first derivative with respect to moving the left endpoint. AB minus B. I said, AB minus, did I do this wrong? Oh, yeah, that's right. Sorry. Say it again. Okay. ABC minus BC is the first derivative with respect to moving the left endpoint. AB minus B is also a first derivative with respect to moving the left endpoint. Therefore, this whole combination is a mixed second derivative with respect to moving the left and the right endpoints. So the mixed second derivative is non-negative, non-positive according to strong subadditivity. And in particular, if we have translational symmetry, which we've had in all the cases we've been considering, that simply applies that this, as a function of L, is concave. Okay? Yeah.
Suppose A was like epsilon and B, C was epsilon C.
Yeah.
And the right technique for
Epsilon A times epsilon C. This one would be epsilon A, this would be epsilon A, and this difference would be epsilon A times epsilon C. Okay, so this is great, but we can actually make a much stronger statement if we include relativity in the game. So far, this statement follows from SSA plus translational symmetry. I could have a non-relativistic system, and it would obey this. But if I bring relativity into the game, I have a more powerful statement. Because I can start moving my intervals A, B, and C in a very similar construction up and down in time. So I'm going to do the following thing. So first I'm going to make the statement that for a single interval in the vacuum of a relativistic theory, relativistic QFT, S of A depends, so because we're in the vacuum, the state is itself Lorentz invariant, and I'm in 2D. And I have a single interval, so I have a proper length, proper distance between the endpoints. That's the only Lorentz invariant quantity that I can derive from an interval. So it doesn't matter if my interval looks like this. This is not allowed to go more than 45 degrees. It doesn't matter if my interval looks like this. The entropy is just a function of the endpoints, of the proper distance between the endpoints. Okay? So now let me consider this configuration, where I make A, B, and C look like this, and these are null. A and C are null. Now, you may worry, should I really be considering S of A and S? Don't worry, I'm not going to consider S of A or S of C, I promise you. I'm only going to consider S of B, S of ABC, S of AB, and S of BC, the things that enter into this formulation of strong subadditivity. Okay, so I'm not going to, S of A is not entering into this. In fact, in some sense, A is not entering, only AB and ABC. Those are the only things, including A, that I care about here. Now you can, it's an easy exercise in Minkowskian geometry to show that this length, the lengths of these things obey this relation. That means, so then SSA implies, so here, using only the translation symmetry, it implied that the entropy was a concave function of L, where I implicitly used the fact that the length of ABC is the length of AB plus the length of C. In fact, what I used here was, what I really used was LABC plus LB equals LAB plus LBC. And now we have a very similar relation which holds not for the L's but for their logs. So by the same logic, S is concave as a function of log L. Log L. It's concave as a function of log L. From translational symmetry, it's concave as a function of L. From Lorentz symmetry, it's concave as a function of log L. And that means, in turn, or that's the same as the statement, that the first derivative of the following function is negative, where C of L is defined as 3L, well, let me write it this way, 3 ds of A d log L. So compute S of A as a function of L, take its logarithmic derivative, multiplied by 3, and this is the statement, this statement here is the statement that the first derivative of this function C is non-positive. And that means that if I have some kind of RG flow that connects two fixed points. In the UV, my theory looks just like some UV CFT. And for a CFT, so for a CFT, C of L is independent of L and equals its central charge, because this is C over 3 log L. So this is C, independent of L. So for an RG flow, C over L goes to the central charge of the UV fixed point as L goes to 0, and it goes to the central charge of the IR fixed point as L goes to infinity. So it's going to look like this. In between, it can only decrease. Let me, in fact, so this implies that CUV is greater than or equal to CIR. So this is a proof of Zamolodchikov's C theorem. And I want to point out that the ingredients that go into the proof are the same as Zamolodchikov's. So Zamolodchikov proved the same result by considering correlation two-point functions of the stress tensor in Euclidean space. And he assumed that the theory was unitary, which meant that the two-point functions in Euclidean space obeyed positivity, reflection positivity, and that they're conserved. And from that, he was able to deduce the same relation. The ingredients here are the same. Oh, and he used Euclidean, the Euclidean group, okay, the Euclidean version of which assumes that the corresponding Lorentzian theory is Lorentz invariant. Here we use Lorentz invariance, but we work in Minkowski space, and we assume unitarity that goes into strong subadditivity. So the ingredients are the same and the result is the same. The proof in the middle looks totally different. And furthermore, the C function, so Zamolodchikov defines a C function as a function of distance and proves this same inequality, and his C function has these properties, so the logic is very similar, but the C function is different. Some other decreasing function that has the same values at the endpoints. Okay? Yeah.
Also, locality has to be used too, because I think your counter is like and only the one without locality.
Right, and so then, yeah, I mean, so that's existence of a stress tensor, I guess, for Zamolodchikov. And here, I think it's probably in at least one place where it enters. We're assuming that S of A is C over 3 log L, and that's probably not true. I don't know. I mean, what class of theories we would include? Yeah.
So are you saying that along the RG flow is a completely different function? It just happens to be the same?
Exactly. Exactly. And they're both decreasing. Yeah. Mm-hmm.
But they're not related in any...
They're not related in any sort of... yeah, I mean, for example, you can take any C function. If we define a C function to be one which obeys these three properties, this one, and this one, you can take any C function and do a convolution with a positive kernel, and you'll get a C function. But these are not related by convolution by positive kernel. So they're not sort of related in some simple way like that. Yeah.
So LAB is the square root of the proper distance.
It's the proper distance between the endpoints. Mm-hmm. That's an exercise for you. So that follows from these being null and a little bit of Lorentzian geometry. Yeah. Well, strong subadditivity works. I'm not sure what you mean. You know.
I mean that.
Oh, I see. Right, right. And in fact, that's probably another place where I used locality in this. Indeed, the assumption that the degrees of freedom kind of that you have independent degree Hilbert spaces here, here, and here that you're doing a tensor product on. You need that for strong subadditivity. There's actually a version of strong subadditivity. If you want to work in algebraic quantum field theory, you can express strong subadditivity without having this Hilbert space decomposition. And then I believe it's true, although I don't know if this has been written down anywhere, that you can write down this proof in that formalism and never actually, so you would have a definition of C of L which never requires this divergent function entering an intermediate step and which doesn't require the tensor factorization. Okay, so okay, so what I want to do now is higher dimensions. So far we've been in 2D. Yeah. And the story is similar. Yeah.
Is there a definition, notation of entropy for A?
I don't think so because the proper length of A is smaller than the cutoff.
But A belongs to some
No, it doesn't really have a causal domain. A doesn't have a causal domain. I mean, its causal domain is degenerated. Yeah. Yeah, it's itself. Yeah, I mean, I suppose if you wanted to, you could do this as a limit, but you never care about S of A in this. That's very important. That never enters into this. No, if you want to, no, but then I would be careful. I mean, that is probably not well defined, because once the proper length of your interval becomes smaller than the cutoff, it's probably not well defined. So one, I mean, I should say that there, a caveat in this, where people are usually not super careful, is there's an assumption in this statement. So we agreed that the entropy depends on the cutoff, and the assumption here is that the cutoff can be implemented in a way that respects Lorentz symmetry. And that's probably not true. So there probably doesn't exist a regulator which respects Lorentz symmetry and maintains unitarity of the theory. So that's sort of a caveat in this proof, and the way to get around that is by using this algebraic quantum field theory, which never appeals to a cutoff. Yeah.
I thought this paper proof of quantum was so bad that use the entropy of just light sheets. They just like that when they talk for trillion.
Yeah. I mean, I don't know how careful they were being. Yeah. 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 Yeah, but even that, I mean, I think, yeah, depending on what quantity you're taking the limit of, one should be careful. Not everything in this field is really super well understood. If you want to, like, redo what other people have done in a more careful way, there's there's ample opportunity to do that. I mean, that's not usually considered like a very sexy thing, an exciting thing to do, and so there tends to be a lag between, you know, the first time somebody does it and the first time somebody does it carefully. Okay. In higher dimensions, well, let's just say I'm just going to stick to a CFT with A being a ball of radius r. And then, so yeah, I have some. And then, again, by similar logic as before, I have my modular Hamiltonian being this. You get this formula. So, and what is this? This is a generator, again, of a conformal boost, which acts on the causal domain, causal diamond of this in the same way as before. Or in Euclidean space as a rotation about the entangling surface. And one other thing to say about this, which is also true in 2 dimensions but gets more interesting, is a more useful statement in higher dimensions. So I already said that this is conformal to, the Euclidean version is conformal to a sphere, but this is also conformal to HD minus 1 times R if we're doing Lorentzian, and S1 if we're doing Euclidean. So that means that rho sub A is under a conformal transformation a thermal state, an honest thermal state, not with respect to some funny Hamiltonian, but an honest thermal state with respect to just uniform time translations. So at uniform temperature, 1 over 2 pi on hyperbolic space. Not hyperbolic space-time, not ADS. Certainly not ADS-D, but I have just a hyperbolic space, uniform, and at a uniform temperature. Okay? And the interesting thing is that under this conformal transformation, you see, I had let's call it a disk. Let's say we're in 3 dimensions. I had this disk, which I've mapped to hyperbolic space. And what was a UV divergence of my entanglement entropy as I approach the entangling surface now becomes an infrared divergence. Simply, if I try to evaluate the entropy of a uniform thermal state on the hyperbolic space, of course I get infinity because hyperbolic space is infinite, has infinite volume. So that UV divergence under this conformal transformation turns into an IR divergence. And another interesting fact here is that the same conformal transformation, if I extend it out beyond this disk, transforms, so the same, or the extension of that conformal transformation takes the complement of A also to hyperbolic space. So that what that means is that the vacuum in the original theory on the original Minkowski space is the thermal field double of the thermal state on A. So this is the vacuum on the full system, A complement. It's a pure state. It's a pure state which has the property that if I trace out A complement, I get this thermal state, this one. And also if I trace out A, I get the thermal state on the complement. That means it's the thermal field double. Yeah. How what? Yeah, I mean, A under this conformal transformation takes A to, yeah, but you're right. Okay, so let me be more careful. The thermal field double of the thermal state on HD minus 1 is equal under a conformal transformation to the the vacuum in the original frame. Okay, now so that's one interesting. If you want vial frame, in other words, there's a vial transformation which maps this to hyperbolic space, but there's another one which maps it to a sphere, which we already saw, and that is actually very useful in higher dimensions. You can use it, as I said before, in 2 dimensions, but in 2 dimensions you have so many different tools. I wonder if it's here. Here it is. Awesome. Okay, voila, this is now in higher dimensions. And now we have to ask ourselves, what is the, so we still have this equation. Okay. Can I have a minute? Coming to a punchline. So, what we have to do is we have to evaluate the partition function on the sphere, okay? And in 3 dimensions, the interesting thing is there's no Vial anomaly. So the partition function, there's no transformation between this and this. And then you ask yourself, okay, what is the partition function on a 3 sphere? And in 3 dimensions, the partition function on a 3 sphere has the following form. It's, of course, a UV divergent quantity. But the divergences, if you think about their structure, look like this. Basically, you can follow the divergences from the possible counter terms you can write down, you can add to the action. You can add a cosmological constant, and that shifts C3. You can add an Einstein-Hilbert term, and that shifts C1. So these guys are non-universal. But there's no local counter term you can add to the action that changes the constant term. And it turns out there's no R squared term either. So this guy is universal. It's called F, and it characterizes the theory. And so by virtue of the equality, so somehow under this equality, this term goes away, and you get S of A, because we know that the leading divergence is proportional to the area, which in this case is just a length because we're in 3 dimensions. So we get C1 R over epsilon minus F. And so if you can calculate this as a function of R for circles of radius R, then you can extract F from the entropy. And I'll talk about an application of this next time, but I'm over by a few minutes, so let me stop here. Yes. Somebody, yeah. That would change F? No, I don't think so. I haven't thought about it, but it must give you, I don't know what power of R. Yeah, I don't know off the top of my head.
Okay, the four-point function of twist operators, what's the data?
Everything, yeah.
But is there a limit where it can?
Actually, let me defer this question because I'll talk about the case when you care about that next time. Yeah, yeah, yeah.
Can you use entanglement entropy to hopefully prove the ACR?
Yeah, I'm going to talk about that tomorrow. Not much, but the answer is yes, it's been done. Yes.